Okay, so what we're going to do now is we're going to prove Pythagorean theorem. So what is Pythagorean theorem? The first thing is that what we're going to be talking about are right triangles. So what I drew here was any right triangle. This green triangle that I'm outlining now in blue is any right triangle. And the statement can be stated in a few ways, right? You could say, and we're going to state it the way Euclid did, more or less, 2,300 years ago. We're going to state it more or less in that way, which is just to say that if I draw a square along this side of the triangle, and I draw a square along this side of the triangle, and of course a square along the third side, the square that's opposite the right angle, the square that's along the hypotenuse of the right triangle, this is the hypotenuse, this side that I just am outlining, that side is called the hypotenuse. The side that is opposite the right angle is called the hypotenuse. The square that's drawn on that side, okay, its area is equal to the area of this square on the other side plus the area of the square over here on the other side. So the sum of the areas of let's say, we could say S1 plus S2 is equal to S3. That's a statement of Pythagorean theorem. Okay, if S1 represents the area, right? So let's say S1 is the area inside here, S2 is the area inside here. Then S3 is, if I take the two areas and I just combine this area inside here, S3 is S1 plus S2. That's a statement of Pythagorean theorem. That's more or less the way it is that Euclid stated it in his Elements. And we're going to prove it exactly the way Euclid proved it, more or less. This is the argument that was made by Euclid. So what we do is we draw these two triangles. So let's just talk about these two triangles, and then we'll see how it is that they are relevant. So let's take this green triangle right here to start. Let's look at this. So this green triangle right here, and then what I want to do is I'll draw a pink triangle right here like this. And my first step in reconstructing or redoing Euclid's argument is to say that these two triangles are congruent. Okay, because of course if the two triangles are congruent, then their areas are equal. And that's the real thing that I need. I really need to say that these two areas are equal. But okay, let's first prove that they're congruent. So this is a square. Let's do a nice color here. I don't know. Let's say okay, this square, right? This is a square, right? I drew that square along this side, right? Now, since that's a square, all of its sides are equal or congruent, right? So I have that this side right here is the same as this side right here. But if you look, this side, right, is in that purple triangle. And then this side over here is in that green triangle, right? So you kind of want to like pick up the purple triangle and like turn it a little bit, and you'll see that if you're careful, you'll see that it'll map perfectly onto the other one. And you could kind of say that this one is the same as this one because, again, this is a square. This thing that I'm outlining now is, again, a square. And now, again, if you turn this side, right, of this purple triangle, and you turn the purple triangle so it overlaps onto the green triangle, you can kind of see how these two figures are congruent. The last thing, though, that I need to rigorously show that these are congruent is that let's see this angle, right? This angle, I'm just highlighting it, right? This angle 1 right here in that corner is part of, so Okay, so look at angle 1 and the 90-degree angle. We should see that this orange angle, this whole orange angle, is the 90 degrees plus that angle 1, which is in the green triangle. Now, if I look again and I say this here, this is a 90-degree angle, plus angle 1 is in the purple triangle. So that this whole green thing from here to here is in the purple triangle. And we should convince ourselves that 90 plus measure of angle 1 is going to be the same as 90 plus measure of angle 1. Look, in the green triangle, I have that orange-yellow angle, right? That's 90 degrees plus measure of angle 1. And then in the purple triangle, I have the 90-degree angle with measure of angle 1, making this green angle right here. And if you look at this, that'll kind of tell you that it's side, angle, side, to show that these two triangles, the purple triangle and the green triangle, are indeed congruent, which means that their areas are equal. So we want to write that. We want to say this guarantees area of green triangle equals area of purple triangle. Now from here, I have I'm gonna build on this, but let's go a little bit in the let's shelve that. Let's keep this in our minds. We know that these two areas are equal. Okay, that's good. We got that. Now what we want to do is I want to draw a line from point P that's parallel to this side, or even perpendicular to this one down here. And we know we can do this from our axiom. So I'm actually going to do this in a different color, so it's a little bit more clear maybe. Let's see what would be a good color that would really contrast with everything. I think if I went like that. Yeah, okay. So this line here going down, right, such that this forms a 90-degree angle, right? So from that point right there going down, so that way this forms a 90-degree angle, what you'll see is that we have a rectangle right here. And I'm going to shade that rectangle and then erase it real quick, just so I don't get too confused of what's happening here. Well, maybe not. I don't know necessarily. So look at this rectangle that I just shaded. And I'll cross shade it. And what I'm going to show is that the area of that rectangle is twice the area of the purple triangle. Okay, so that's what we need to now convince ourselves. So we want to show that 2 times, or let's write it in the right direction, 2 times the area of the purple triangle is equal to the area of rectangle 1, let's say. Area of rectangle, and let's call this rectangle 1. Okay, I want to show that. Now, how am I going to do that? Well, if we look at this triangle, right? So let's look at this purple triangle right here. And we just need to convince ourselves that if I draw, right? So imagine this line sort of being extended, right? And I draw the perpendicular, or the altitude, right? The point from down here that's going to form a 90-degree angle, right? And we look at this. This is like your H, right? In your height for a triangle. And this is the base. But this H here is the same as this H right here. And that takes some time to see. Okay, so let's do it again in a different color, maybe a bright color. Okay, or better yet, let's get this. Let's do this. So let's look at this h again, right? And if you see that this is the same as this, right? What's the area of this rectangle? B times h. The area of the triangle is b times h divided by 2. So 2 times the area of that purple triangle will be equal to the area of this rectangle. So now I've got this one. That's good. And now let's look at this area of the green triangle. So let's erase some of our construction marks. I'm going to have to erase some of that, but that's okay. Let's erase some of this so it's a little bit more clear, so not everything is all over the place. And let's look at this green triangle here. So this green triangle, right? If you extend this side, so I'm making it in blue, the side I want to extend. If I extend that blue side, or I draw that line continuing, and then I draw the line that's perpendicular to that line over here, right? This becomes an H. Okay, that becomes some H. And let's make this darker. I think it'll come through better. Maybe? Yeah, okay. Now, this is some H. We need to convince ourselves that that's the same length as this right here. Okay? That's H. And then I have this here as the base. This here is my H. So the area of that square is base times height. And the area of this triangle is base times height. The area of the green triangle, right, which I'm going to shade in this dark blue, right? If we look at this triangle, the area of that triangle is base times height divided by 2. So now I have another statement. I have that the area of square 1 equals 2 times the area of green triangle. Okay. And I have now pretty much just proven the statement, at least half of it. Oops. I've proven the statement, at least half of it, because what I have now is that if you multiply by 2, you can see that I know that the area of the purple triangle is the same as the area of the... I know that the area of the purple triangle is equal to the area of the green triangle. So if I multiply by 2 here, we should see that these two things are equal, right? So you can make an argument, right? You could just go, okay, area of the green triangle, 2 times the area of the green triangle, 2 times area of green triangle is equal to, right? Because of this one, it's equal to the area of square 1. And then 2 times the area of the green triangle is equal to 2 times the area of, so I have this, 2 times the area of the green is equal to 2 times the area of the purple triangle. So I'm using this, right? Because I have, again, 2 times the area of the green triangle, I use this one. 2 times the area of the green equals the area of square 1. I just made that argument from, let's say, statement 1. I don't know. And then from statement 2, this one up here, I have that the area of S1, right? I have the area of the green triangle equal to the area, 2 times the area of the purple triangle. And then my last statement is that the area of the rectangle is equal to 2 times the purple triangle. So this is the purple triangle. So then this is the area of the rectangle. And I'm just going to call it R1, rectangle 1. And this shows, in particular, the key relationship that I wanted was that the area of S1 is equal to the area of rectangle 1. That's the one that I cared about. I showed that this area is equal to this area. Now, this is half of it, because the other half is to show that this area and this rectangle is going to be equal to the area of this square. And then you're done, because you showed that the area of this square plus the area of this square is equal to the area of the entire square over here. And the argument is literally the exact same thing. So let's just go through it again for more practice. You know how to make one half. You can make the other half by just making an analogous argument. Let's go all the way back. Let's erase everything so that way we can do this again. Oh, I can't go back any further. Wait, why not? Oh, okay. All right, it's okay. So we'll draw the picture again. Let's get another one up here. Okay. Okay, so again, you just draw the triangle. So you draw some triangle, and then what you do is you draw the squares that are going to go on either side of it, on any side of it. I'm drawing it bigger this time, which is probably what would have been nice. But again, you want to make the argument. Make sure we know what argument we want to make now. We want to make the argument. I've already shown that this square is equal to. So when I draw this line going down, this line is the key line because it breaks up this square into two rectangles. I want to show this rectangle is equal in area to this square. And I make almost the exact same argument, but on the other side. So the first thing you want to do is you want to draw these two triangles that you want to show congruent. So you want to show this blue triangle is the same as this green triangle. And what does it look like? It looks like this. This is the green triangle. Now, you show those two congruent. You show that the area of one of these is twice the area of one of these is equal to, the rectangle, and then twice the area of the other one is equal to the square. And then you know that the twice of each of those is the same, so then therefore the area of the rectangle is the area of the square. Yeah, what does that mean? Let's go through it again. Okay, so let's get that these triangles are congruent. This side is for sure congruent to this side. So that green side is congruent to that blue side because this is a square that I've constructed. Now this side is congruent to this side, okay? Because again, it's a square. So that side, this side is part of the blue triangle. This side is part of the green triangle. And the last thing that I'm going to say is that if this is angle 1, and we know this is 90 degrees, we know that this is 90 degrees, right? Let's look at these two angles. Let's look at this purple angle right here, and then let's look at this yellow angle right here. Okay, this whole yellow angle, right? Those two angles would be congruent. And the yellow angle is part of the blue triangle, and the purple angle is part of the green triangle, and both of them are the inscribed angle, right? It's in between the two congruent sides. So by side angle side, these two triangles are congruent. Now the next thing is to show that if the two triangles are congruent, then for sure their areas are equal. So let's say area of triangle 1 equals area of triangle 2. That's my first statement. Or really, what is it? It follows from the fact that the two triangles are congruent. Okay, so we would have to say the two triangles are congruent, therefore their areas are equal. Now the next thing, okay, I want to show that this green triangle has the same area as this, has the same, is half the area of that rectangle. So how do I do that? Or what am I saying? Let's go through what I'm saying here. So if I extend this upward, right, that line going up, right, and I draw, look at the green triangle, and I draw the altitude from over here, right? This is some height, let's say. But we should convince ourselves that that h is the same as this h. And if we look at the green triangle, this side that I'm outlining now in this orange, right, this is the base. And base times height is for sure the area of this rectangle. Okay? And that means that the area of, let's call this triangle 1, the green triangle, whatever, the area, 2 times the area of triangle 1 is equal to the area of rectangle 2. So 2 times area of triangle 1, and that's the green triangle, is equal to area of rectangle 1. And with that, then I show, so now I'm going to show something slightly different. So I should have erased the construction, but it's okay. Let's go back. Let's get these construction marks off. And now let's show something else. So what did I show? I showed that, so I have this, that's already done. And now I just showed that 2 times the area of triangle 1 is equal to area of rectangle 1. Of rectangle 2, because the other rectangle is rectangle 1, rectangle 2. Okay. Now what I show is that if you look at this this one, right? Or wait, how do I want to look at this? Okay, I got it. You see, it takes some time. This here is the orange side, right? Extend that side in the blue triangle. So this is we should see the blue triangle. Look, identify where that blue triangle is. Look at this orange side. Extend it. Okay? And then drop down this perpendicular, right? And we need to just convince ourselves that this, right? This is H. This is H. If this is H, this is the same thing. I didn't draw it that well, but you should see that this length is the same as this length. And this is the base. So the blue triangle area, right? Take your time, look at this picture. The blue triangle area is base times height divided by 2. And the area of the square is this length times this length. And that will give me the fact that 2 times the area of triangle 2 is equal to the area of square 2. And with these 3 things, just like in the last one, okay, I can show that this area, this rectangle's area, is equal to the area of this square. Because I just sort of like play leapfrog a little bit, or I just move this stuff around. Look, 2 times the area of triangle 1 is equal to 2 times the area of triangle 2. So let's have that in our minds. 2 times area 1 of triangle 1 is equal to, well, what else is that? That's equal to the area of rectangle 1, or of rectangle 2, of R2, okay? And I know that that the 2 times the area of triangle 1 is equal to 2 times the area of triangle 2. So I'm going to write from here, 2 times area of 1 is 2 times area of triangle 2. Then I know from this one, from this statement, that 2 times the area of triangle 2 is the area of S2. and I have the statement that I want. The statement that I care about is that 2 times the area, or that the area of rectangle 2 is equal to the area of S2. Because putting this all together from the previous one, we should convince ourselves of the following. I just showed previously that this area, the rectangle, the area of this rectangle is this one, right? So the area, this is S1, right? The area of this piece, rectangle 1, plus the area of rectangle 2, is that the area of the entire square? Yes. So square 3 is equal to the area of rectangle 1 plus the area of rectangle 2. I just showed that the area of rectangle 1 is the same thing as square 1. And I showed that the area of rectangle 2 I just more recently showed that the area of rectangle 2 is S2. And then this is the statement of Pythagorean theorem. And this is how Euclid did it 2,300 years ago.